Hello everyone. I am Today we'll be taking up the fourth unit, that is the data converters. These data converters, why they are of importance in the analog mixed VLSI design, and then what are the different types of data converters we study, what are their specifications, how these specifications are considered, and we come out with the mixed signal layout issues. So these concepts we'll be studying here. Initially, as we see these data converters, what happens is in the real time, the signals that appear, they are analog in nature. But looking into the various advantages in terms of the memory, speed processing, and the mathematical equation the processor designing, with respect to all this, we find that digital systems are more advantage while during processing of the signals. So what we do is, whatever the analog in nature signals appear in the nature, they are converted into digital form, processed, transmitted, communicated, and finally we get back the analog signal from these digital signals. So as we see at the one end, if we are going for the analog to digital conversion, we require the digital to analog conversion at the other end. Therefore these two types of data converters exist in the communication and various other applications. So here the thing is, how do we convert this analog signal into the digital signal? Before exactly we go for the digital signal, these analog signals are down converted into discrete time signals. There exists, try to understand the difference between discrete time signals and the digital signals. The digital signals will have either zeros or the one values, whereas discrete time signals will have the discrete values. For example, now suppose we have a signal with a peak amplitude of 5 volts. That means its value ranges from 0 to 5 volts. So suppose if we have an analog signal, for example, take my speech signals itself, whatever I am talking now. If these signals has been plotted, there will be a continuous plot of the signals for every instant of the time. That becomes an analog signal. Now suppose if I go for reading this, once I plot this analog signal, if I take the reading of the same speech signals at every time instant of 1 second, then from 0 to 5 volts is the range. In that one, the values will be, might be whatever the amplitude pitch, values of the signals for every second, it might range from, like, it may be 0, it may be zero point 0.5 volts, it may be 1 volts, it may be 1.5, 1 or 2, like it varies, so it may vary up to 5 volts. So the what we are doing here is, instead of taking the readings of the signals for every time instant, instead we take these values for the different time instants with the different amplitudes. That's what we come. So that is what is a discrete time signal. So the difference between analog signal and discrete time signal is, all the ranges of the amplitudes will be taken, but in case of the discrete time signal, only at the particular time instant the readings are taken, whereas in the analog signal, the signal exists for every time instant. So this every time instant, when I say, the instant might be in terms of second, millisecond, microsecond, nanosecond, to still if you go for the smaller versions, still there the signal exists. So this is all about the analog to discrete time signals. But how do we exactly go for this discrete time signal conversion? Actually, the general block diagram is shown in this particular slide. You can see there the analog signal, which is shown as a sine wave, it is passed through a low pass filter. Always we go for the low pass filter. The reason is, we want to limit the signals that we are processing. Again, I'll take the example of the speech signal itself. The audio range that is standard defined to be 20 hertz to 20 kilohertz, but actual process, whatever the speech signals, they exist only between 300 hertz to 3.4 kilohertz, and this is what is the exact bandwidth which is also considered in the all the telecommunication applications. So as we see now, the signals required between 300 hertz to 3.4 kilohertz. What we do is, we put a upper cutoff frequency to be 3.4 kilohertz, collect all those speech signals, and then go for processing. So we require a low pass filter because low pass filter has the higher cutoff frequency. Once these signals are passed to the low pass filter, we are concentrating on the signals that are required. So the frequency is limited. Further, it is applied through the sample and hold circuit. This sample and hold circuit plays a very important role as it reads the analog signal and then holds it till the further processing is done. And exactly how the specifications and what is the circuit diagram we'll see into the later topic. Finally, once the sampled and whole circuit output is done, we get that is been given for the analog to digital conversion. The exact reverse process is carried out at the other end in order to get back the analog smooth signal. So this is about the analog versus discrete time signals. Next one is how do exactly we convert. So that is what is we shown as the discrete time signals. But now if we want to get the digital signal, as I told you, discrete time signals means it is not the zeros and ones. It is all about we have the values which are ranging from 0 to 5. So now we see how exactly we convert the analog signal into the digital signal. This we can explain considering the real time scenario. Now, suppose we give an example. We have a problem where the problem states is we want to see the weather report of one complete week, wherein we will be taking the readings every day, whether it is a hot or it is cold that we want to find out. So, in order to do that, what all things are what all things are required initially, as we see now. How many readings we take during the given span. As we said, we want to take the readings for one complete week, and in that case, so 7 days are there. And each day, how many readings do we take? So that is to be decided. So once we decide that, next thing is I require a thermometer. This thermometer, so how many readings are available on that thermometer? That will also play a role in deciding whether it is cold or hot. Because see, suppose there are only two readings. We take the ratings on the thermometer are in terms of Fahrenheit, suppose. So there are only two readings. One is 0 degree Fahrenheit and ultimately another one is only 50 degree Fahrenheit. Intermediate values are not marked there. So in that case, whenever I use this thermometer twice a day, so then it takes two readings. Let it be at 12 o'clock each. So mid afternoon 12 o'clock and midnight 12 o'clock. So midnight to 12 o'clock, there it will be cold usually, and in the afternoon it will be hot. So then what we see is there are only two readings, 0 degree or the 50 degree. Then either it will be hot or the cold, and the same thing will almost repeat for every day. So as we are observing here, there is suppose if it rains also during the daytime, still it is a sunny day as compared to the night. So then there will be a it will be comes under the hot day only. So the data is not exactly clear to understand it. Now suppose what we do is instead of taking only two readings, I will make it as a four readings on the thermometer. Let it be 0 degree Fahrenheit, 12.5 degree Fahrenheit, 25 degree Fahrenheit, 37.5 degree Fahrenheit, and finally 50 degree Fahrenheit. So in that case, what I am observing is now suppose due to the rain, if it is around 12.5 degree Fahrenheit, so it comes under the second range. And in case suppose if I mention that to be the cool, not as a cold. So that case, I am finding it out. It's a cool day, not exactly a cold day. And the same way, suppose in the midnight, and due to this humidity, if the temperature instead of being mm, around, if it is instead of being like it is somewhere around 20 degree Fahrenheit. So what I am finding it is that it's again a cool day, not a cold day. Previously either it is a cold or it is a hot. Now I am seeing if it is a cool day means somewhere it is lying between these two degree temperatures. So we are getting more clear information. So as we are seeing, as we are going for taking more levels of the same 0 to 50 degree Fahrenheit, as we are taking more number of levels, the information clarity is increasing. This is about the levels. Now suppose if I go for the 8 levels, more clear with the information will be. So this is what is we say are talking in terms of different levels. This itself we call as the quantization levels. Now we speak in terms of number of readings. So as I said, we are taking 2 readings per day. Instead of taking 2 readings per day, if I mention for every 3 hours we will be taking the readings. So in one day, how many readings we are taking? We are taking, so for every 3 hours means we are in total taking 8 readings. So that means we take 8 readings, we find out what will be the temperature, we take a average of it and we assume something hot day or the cold day. Then as we are observing here how many samples we are taking per day and in how many levels we are reading these values. These are making the information clarity. As we take more number of readings, clarity of the information is more. So this is how the whatever analog signal is there, it is read in terms of number of quantization levels and number of readings which we call as sampling. So that's what is this complete idea of the sampling rate and the quantization levels is described in the form of a Nyquist criteria, and this Nyquist criteria tells that the sampling frequency should be minimum or it can be greater than the 2 times the maximum frequency of an analog signal. So Fmax actually stands for the maximum frequency component that is present in the analog signal, because the analog signals, as we see sine wave, one particular frequency is defined, but in analog in nature whatever the natural signals occur, they will not be having one frequency component, they will be having a multiple number of frequency components. So we take a maximum frequency and we define the sampling period for that signal. This is stated by the Nyquist. So with this I will be stopping. In the next video I will take up the sample and hold circuit. Thank you.